Hello everyone. This is a special edition for physics or about physics, about rotation of rigid objects, about a fixed axis. So yes, you are not misheard. I switched from math to physics per request of one of my students there. Okay, and that's done specifically for him, and other students can also use that and utilize this concept. So today we're gonna go through rotational dynamics, and we consider angular displacement, velocity, acceleration, and also we are going to consider rotational dynamics in terms of kinematics. So what rotational kinematics is behind rotational motion. Okay, so everyone like physics and want to understand this concept, so welcome. But make sure before you need to get acquainted with a circular motion and of course with standard linear kinematics. Okay, on one axis or along one axis and also in two dimensions. So you need to know and get familiar with those terms, because there I'm going to use to put analogy with the circular motion and with rotational kinematics there. All right, so before we need to give a definition of what rigid body is, because in context you have a rigid object. So rigid object is any object within which two or more taken particles are not going to change position within relating to each other. It means that no matter, let's say this is the flat body depicted with this curve, that's curvilinear shape, no matter what sort of shape, let's say that's very thin 2D shape, so that we can completely put on y-axis. So this is x-axis there. Okay, so what it means that it would take two different points, let's say point 1 and point 2. So the distance between them is not going to change during rotation. Basically, distance keeps the same no matter how long it's rotating, with which velocity it's rotating, linear velocity or angular velocity, it doesn't matter. So the distance is not changing between them. Basically, separations keep the same for all particles within that body. So that's what is called rigid body. Okay, you can assume that the distance between atoms or molecules of this body are not going to be changed. That's why it's called rigid. So rotational dynamics of rigid bodies is very simplified version of those. If we consider it semi-rigid bodies, so that the distance might change during rotation. We are not going to discuss within this course, so make sure you understand that. So okay, that's the 2D shape of rigid body. So I hope you understand this concept. And in order to keep track of rotational motion, we need to keep track of different particles. So we can take any random particles, let it be right there. So particle P. So what we can use in order to describe the position of that particle. So if rotation occurs along the perpendicular z-axis that looks on from the plane that you can see from the plane of the paper or from the plane of the board onto you, so that's the axis in 3D. Rotation goes in the anti-clockwise position, so let's say this way around. Okay, so this is anti-clockwise. In this case, we are keeping track of that point, and we can set up the position vector. That's normally how we can use to describe the position of point P. So we can use the polar system in this case, so polar system or polar coordinates in order to describe the position of the point P in any given point of time. So that's why you remember that means we need to keep track of the position vector r. So, and also we need to keep track of the angle theta. So this is angle theta of rotation, okay? So we measure it from always from horizontal x-axis, and those pairs basically can be considered as their equivalent for the xy system. So if you like, you can always switch from polar coordinates into the Cartesian coordinates xy, because using just basic trigonometry. Okay, so we are going to keep on track, and let's assume that point P that was originally, let's say here, change the position, so that's point P at the time instance t equals 0, and now point P is right there at a given moment of time t. So as you understand, the radius, the position vector, rotated or turned in anti-clockwise position by the angle theta. So what can you say about the curve, or the part of the curve that your point P is going? So all tracks are pure circles for any given point relating to the axis of rotation. So basically, it's going to be a set or family of concentric circles which describe the path, or which describe the path of any given point P. Okay, so that's why it means that per time t, the s distance or the s arc length that point P travels from that position to this position can be described using the basically arc length. So this is arc length, and you can describe using basic idea of how to work out the arc length, having a distance r and angle theta. In this case, angle theta should be in radians, okay? But if you're given different angles in degrees, you can always switch on to radians by using the idea that in pi there is 180 degrees. So that's why if you want to convert your given value for, let's say, 30 degrees, you simply can take pi over 180 and times your given angle, let's say 30 degrees. That's how you can convert into radians quickly if you're given theta in degrees. Okay, so that's an idea, and for per time theta, the point P will cover the arc length S in this case. Of course, you can put a displacement vector if you like, but more properly to use as arc length. So from there, we can express angle theta as S over R. Okay, and it's going to be in radians because both arc length and radius will be measured in unit of length, like in meters and so on. So that's why it will be cancelled. So basically, radians is sort of artificial units. It's not real units. It's nothing actually. Okay, so that's an idea how we can express displacement from there. Okay, but let's have a look at another case. We have a pure motion. Again, we set up the system of coordinates x, y, z. And in this case, I want to track a given point P, and let's set up the rigid body in this way. So it's going to be some rigid body rotating around this origin O. So this is y, x, z. And we choose point P that currently stays here. So that's going to be initial angle theta. And due to the time t, this point will be rotated through the angle delta theta. Actually, the new angle right now is going to be angle theta final. So that's why the change in the angle for the point P along the curve or along the arc S is going to be depicted as theta final minus theta initial. So this is the change in the angle, and that what is called angular displacement. Okay? So use an idea that no matter which point you take, P1 or P2 or even P3, because the body is rigid one, the angular speed of rotation that defines, so in average, that defines how fast your angle theta is changing over the time, or over delta t if you like. So that's the average speed of rotation, of angular rotation of your solid, of your rigid body. It shows you basically the rate of change in the angle theta. Okay? So what I'm going to say, that no matter which particles you choose, the omega for each of them is going to be the same at a given point of time, no matter where you're taking that. Okay? Because as you can see, it depends only on the angle theta. There is no radius in this formula, so that's why omega is the function of theta. Okay? And theta is the function of time, as you understand. So that's why finally, we understand that omega is the function of time as well. So omega is the function of time. So no matter, because if you take point here, that will turn in this way. So that's why over a given point of time, over a given period of time, it'll reach the same line, right, where the position vector for the point P goes. So that means for a given point of time, both particles P and let's say particle P prime will be rotated at the same angle. So that's why omega for any given point of time is going to be the same. So omega is angular. This is angular velocity. So this is angular velocity. And because it's velocity, this is definitely the vector. Because this is the vector, how you can measure that? So, how you can measure? You can always measure using the idea of the screw. So let's say you put a screw at the pivoting point. So that's the pivoting point, pivot. And you use the screw to open the bottle, to open the cork of the bottle. So that screw, or screwdriver, doesn't matter. So if you put to the point, you pierce that, and your screw is going to be perpendicular if you have a look from the top, okay? So you're rotating in an anti-clockwise position as the body moves, so with omega, probably depending on time. So you have the rotation this way, and if you pretend that you open the cork of the bottle, so your translational motion will be on you, right? So if you have a look on the flat, so this is 3D case. This is 3D case. But if you have a look on top, that definitely means that your screw will go on you from the paper plane, okay? It goes on you because you're opening. So this is opening. So that's why the positive, so the vector omega will be directed onto you, onto your face from the paper plane when rotating in the anti-clockwise position. So anti-clockwise. So that's an idea. That's an idea. And in this case, anti-clockwise, omega is directed onto you. So that's why the vector omega will go on you. Okay, so that's an idea. But if theta, the rate of change of theta, is not always the same, so you can say you can set up the formula for instantaneous omega. In this case, you need to take the prime or need to take the limit from that. So in other words, you're taking derivative d theta dt. That's the same as limit when delta t is very small. Okay, in this case, you'll take a derivative of the theta with respect to time. Okay, so this is instantaneous angular velocity. Okay, so from angular displacement, we'll go to angular velocity. So this is angular velocity. All right, so if you understand this idea, we can go through what if your omega is changing as well. So if omega is the function of time, and let's say it's not constant, in this case, you'll definitely need to arrive to what is known as angular acceleration. So angular acceleration, so an average, is simply an average how much your omega is changing over the time. For example, pretend that every turn you'll increase your theta of, so you'll increase the angular velocity every time per, like, evenly per certain amount. In this case, you'll have acceleration not average, but it's going to be a state, it stays the same, it's going to be constant. But if omega depending on time differently, so you're accelerating, then you're deaccelerating, so you'll have different values of alpha. So this is angular acceleration. This is angular acceleration. And it shows you the rate of change in omega, in angular velocity. So alpha is going to be the prime. In the same way, you can take instantaneous one. Instantaneous alpha is going to be the prime. Okay, it's also a vector. It's also a vector. And this, how you can have an idea in which direction alpha goes. Because this is the prime, right? If omega is increasing, still we are rotating anti-clockwise, and omega is increasing. So in other words, we have prime positive. So as for acceleration. Or if rotating anti-clockwise, in this case, we also have an idea of positive acceleration. And in this case, we are rotating anti-clockwise and we diminishing the value of omega every time. In this case, we'll have also angular acceleration to be positive in this case. Okay? So when rotating a rigid body around or about a fixed axis, so every particle on rigid body rotates through the same angle, and that's why it has the same angular speed, okay, and the same angular acceleration if the angular speed is not changing, okay. But if it's changing, it changes simultaneously for all the particles. So that's an idea. Okay, so I think that's all for about those physical quantities, about angular displacement, angle theta basically, angular velocity omega, and acceleration alpha. But on top of that, I want to add a bit more. So as we arrived at omega is delta theta over delta time, so on top of that, we can write the following, that I just squeeze a little bit and tell you a bit more. Just remember the formula for the period of the pendulum. So if you have the pendulum, basically suspended rigid body, suspended maybe stone or some load, okay, and you deviate on some angle theta, right? We can come to the idea of the period, yes? It's not necessary for this pendulum, but for any circular or periodic motion that goes in circle way. So it would deviate by the angle theta. We can calculate omega as how fast your angle is changing over time. But for the full oscillation, for the complete period, delta t becomes period of oscillation, and delta theta becomes 2 pi in radians, right? So that's why it's a well-known formula about how angular velocity or angular speed is connected with the period. So in this case, so we have a look at how omega as the speed, as the magnitude of the vector is connected with the period. Or if you want, you can rewrite in terms of frequency, having that t is 1 over frequency, okay? So if you plug there, you'll get another formula which tells you that it's going to be 2 pi f in this case. So this is an alternative formula for the omega. So I hope you understand that, and we can move next. Now we are going to consider rotational kinematics and with constant angular acceleration, and we derive other formulas related to kinematics, okay? And here I'll give you also an analogy with translational kinematics. Okay, so let's get started. Before we found out that angular acceleration is change in omega over time. So in the case, we can say that change in omega, just remember that picture, when it starts from initial angle to the final, we'll have the change in omega in the way final minus initial over time, okay, over time. So this is the way how we can estimate final frequency if we assume that omega is changing gradually, okay? So omega final is going to be, so we can rearrange and just simply express omega final as alpha, is better to write omega I plus alpha t, when alpha is constant, okay? If it's not constant, you need to go to the calculus and say this. This is going to be d omega dt. And now if you want to express d omega, so you need to work out integration like this. Okay? And now you need to integrate both parts in order to arrive to final omega, from omega initial to omega final. That's what you'll get. But you need to know how alpha depending on time in this case. But when alpha is constant, you'll get pretty simple formula that looks like very the same as for linear acceleration. Just remember, for linear acceleration, we have, and not in vector way, but we assume that can be vector or can be components. So V final is going to be V initial plus acceleration, which is in this case tangential acceleration, times time. Okay, so it looks pretty the same. It looks pretty the same. So we can say that in this analogy, that's going to be omega final, that's going to be omega initial, and angular acceleration becomes linear tangential acceleration. So that's going to be alpha times time. Okay, so that's the complete analogy with linear velocity and linear acceleration. Okay, this is linear and this is angular. So we can even more think about how can be theta expressed through, let's say, acceleration. You remember that omega, if we express through the change in an angle theta over time, so we can say that in that case, we know that in order to find theta, we need actually to delta t. So let's assume that we have omega equal d theta over dt. So in order to find d theta, we need to integrate omega dt in this case. Okay, but we know that omega dependent on time in this way. So we can use the formula, let's say 1. So if we plug, instead of omega, formula 1, we'll get the following. So this theta, so both integration, so we can integrate this theta, and finally we'll get the following. So in this case, it's going to be theta final minus theta initial is going to be equal to, when we plug omega I and integrate, we'll get omega t. And when we integrate alpha t by dt, we'll get alpha t squared over 2. Okay? But we can rewrite by transferring theta I to the right side, and that's how we can get omega final will be equal to, theta final angle theta at the moment of time t is going to be initial theta plus omega t and plus alpha t squared over 2. So this is well-known formula for, for what? For how distance or displacement depending on time. Okay, so that's why if we give analogy for linear motion, we'll get the following idea. So we can say that if theta corresponds to the coordinate or to the position vector or to displacement, no matter, let's say to the position vector. So position vector is going to be the initial position vector plus initial velocity vit and plus at squared over 2, which a is the tangential acceleration, as in this case. Okay, so that's why we have a complete analogy, and that's fair for a linear case, and with some transformation it's going to be fair for angular case. Okay, so that's how it works. And what if we eliminate time? So this is formula 2. What if we eliminate time? Let's say express time from the first one and set up time instead of time into the second equation. We'll get equation 3, which will connect actually omega initial with omega final and with the angle theta, or a change in the angle theta. So we'll get the following formula, that omega final squared will be equal to omega initial squared and plus 2 alpha, and here we're gonna have the change in angle theta, okay, from final to initial one. Okay, and in this case we'll get one more formula that connects omega with angle theta. Okay, so this how it works, and I think it's a good idea if we try to have a look at the following example. So here is the wheel. It rotates with constant angular acceleration of 5.5 radians per second. Okay, so we're given, let's copy that just in case we need this for a while. Okay, so, and angular speed of the wheel is 1 radian per second at initial moment of time. So, okay, what are you given in this case? You're given that omega initial is 1 radians per second. So radians per second. Okay, you also got the angular acceleration, which is constant, and it always has value 5.5 radian per second squared. So by the way, comment to the units if you remember how alpha depending on time, yes, and express, so you'll get the units radian per second squared, obviously. Okay, what we need to find? So we need to find through what angle does the wheel rotate in 4 seconds. So you're given a time t equals 4 seconds, and you just want to calculate the angle which the wheel finally have through 4 seconds. Okay, which formula we can use? So obviously we can use the formula that connects angle theta over given time periods. So I just write one more time. Theta final is going to be theta initial plus omega initial time and plus alpha t squared over 2. Okay, so if we plug that into the formula, we'll get a formula. We'll get the following. So initial theta, let me see what we have. Initial theta. We're not actually through what angle? Oh, okay. In this case, we need to find the difference. We're not supposed to find the initial angle. So we need to find the difference. Change in theta. Okay. That's going to be simply omega, which is 1. So t is 4 seconds. So we'll get 4 plus alpha 5.5. So t squared is going to be 4 squared is 16 and over 2. Okay. In this case, we will calculate angle in radians. I'm pretty sure that we can do right now because we everywhere have the same unit. So 4 plus 5.5 times 8. We get 48 radians. So we'll get 48 radians in this case. 4 seconds, yeah, that's okay. But we want, for example, what if we want to convert into degrees? Okay, you just remember that from radians to degrees, so 48 radians correspond to some pi radians as the same as your angle in degrees. Theta in degrees correspond to 180. So that's why from here you can express angle theta as simply 180 degrees times 48 and over pi in this case, because radians and radians will be cancelled and you're left with degrees. Okay, so let's multiply that by 180 by 48, by 180 and divide by pi. Simply divided by pi. Okay, we'll get around 2750 degrees. That's quite big. So by 360 you can calculate even how many revolutions, right? So right now if you divide by 360 you can work out how many revolutions. You'll get around, in terms of revolutions, it's around 7.64 revolution, okay, over this time, over this 4 seconds. That was question A, okay. And in question B, let's go to question B. What's the angular speed at time 2 seconds? Okay, so let's consider that. So we need to find the angular speed over 2 seconds. So in this case, we're going to use the formula for the final speed. Angular speed is going to be initial one plus alpha time. So from where we can calculate that using initial amount 1 radians. On top of that, we're going to add time 2 seconds times acceleration. That's going to be 5.5 times 2. It's going to be 11. So 11 units radians per second. Okay, so that's an idea. That's an idea how we can apply those kinematics. And probably in the next video, I'll show you how to come to moment of inertia and how to, make a full analogy between angular and linear quantities. I'm pretty sure that we need to have a bit separate video for that. So that's enough for now, and I hope you like that. I hope I discovered a bit more and you probably some aspects you didn't know, if it's new for you, or you just can recap it quick and be able now to derive all the formulas there. Thank you. That was Daniel Dallas, and see you next time.